As far as I can tell, grades on Canvas are accurate. If you've got questions about your grade, come talk to me. If you're looking at this exam and going, mother, then we should have a conversation. The thing you need to know is that overall, I'm not unhappy with this grading scheme. This came out with an average in the range I thought it would be in. It came out with a standard deviation around what I expected it to be. I know this is technically not normally distributed. I have the population. I know what this histogram looks like. I will also tell you, I thought that I wrote a relatively decent exam. There were two questions I realized I should have put more words on. In question 7, which is about a uniform distribution, I didn't say the word continuous. So if you did it with a discrete uniform, you got it right anyway. My fault, I screwed up. And in question 9, the last question, I actually took out the wrong question. The first version of the exam I wrote had 14 questions on it. That was way too long. So I got rid of a bunch. And I meant to have you from the Z, not the Z from the X. So I did that. That one was backwards, but that's my fault. So question 8 and question 9 were basically the same question. Apologize. I shouldn't have repeated myself in that fashion. If you have questions about specifics on the exam, the key is posted. Read through it. If you still have questions, come talk to me. If your questions are, what the hell can I do about my grade? The answer is, we can work towards the next grade. Come talk to me. We'll figure out how to do it. Meanwhile, onward we go. So what we were doing at the end of class on Monday, was talking about confidence intervals. And if we knew the mean and the standard deviation, then we could say, oh, I think my results will be around here. And we were able to work both from knowing the population mean and from knowing a sample mean. So let me steal a question out of the textbook again. A 2023 Lexus hybrid is known to have a standard deviation of 1/3 of a mile per gallon. So I know the standard deviation is 0.33 miles per gallon on this car. I go out and I drive this car for a couple of months, and I go through 10 tanks of gas. And in my 10 tanks of gas, I have an average of 41.5 miles per gallon. Now, the problem is I didn't buy this car new, so I didn't get the window stickers. I don't know what the actual manufacturer's miles per gallon fuel efficiency on this car should be. I want a 95% confidence interval. Give me a range of values that you are 95% sure the actual true mean is. I don't have the window stickers. So I don't know what the actual number should be. But I can be 95% sure it's between A and B. How do I find those two numbers? This was the last thing we were doing Monday. Be able to find a low bound and a high bound. How do I find those two numbers? Before anybody spouts off numbers, someone tell me what I'm supposed to be doing. How am I supposed to find these numbers before I actually compute them? I need a z-score. What z-score? Say again? 1.96 is the one that goes with 95%. On our table, if you go back and look in Appendix C, you'll find that 1.96 goes with 0.025. 95%, that means 2.5% is on the outside at the low end and 2.5% is on the outside at the high end. Table C2, 1.96 goes with that number. So I take the average I know, and then I take 1.96 times what? Almost. Say again? No, the mean's here, but it's not the standard deviation. Right, it's the standard error. We call that like sigma with an X bar on it. I just remember this version instead. It's our standard, and on one side I subtract, and on the other side I add. But I know X bar, I know N, and I know the standard deviation. So I can now actually calculate these numbers. It's 41.5 minus 1.96 times 0.33 over the square root of 10, comma, 41.5 plus 1.96, 0.33 over square root of 10. Give me at least 2 decimal places on each of those numbers. The number I get for this side. And this side? I think I got 704, but depends on how far you take it out.
Yeah, it was like 704.
Okay. I'm not going to care about the 100th in either direction. But what that tells me is that the actual miles per gallon I should be getting is somewhere between those two numbers, the true average over all of my tanks of gas. I'm 95% certain is in this range. So if all of a sudden I take my car out and the next tank of gas, I get 31 miles to the gallon, what's going on? Something is weird, right? I don't know what it is. Maybe I did a lot of stop and go traffic. Maybe I did a lot of city driving. And that means that my gas usage changed. Maybe there's something wrong. I got to take the car to the shop. I don't know. But that's a signal that I can now say, oh, I understand. I'm 95% certain when I do a tank of gas and I kept my average miles per gallon, it should be between those two numbers 95% of the time. Questions? The important thing to remember are those critical z-values. The 1.96 came from the fact that I asked for a 95% confidence interval. And right here on page 283, I see, oh, confidence. The confidence gives me this alpha. The confidence is 1 minus alpha, so I get alpha by subtracting. I take half of that, and I go to my normal distribution. And z that goes with 0.05, put 2.5 at the top, 2.5 at the bottom, I get 1.6. 2.5 at the top, 2.5 bottom. I'm sorry, that's 5 at the top, 5 at the bottom. That's 2.5 at the top, 2.5 at the bottom. That's 1 at the top and 1 at the bottom. And there are those three critical z-values. And then I see exactly the formulas we're using. They write z of alpha over 2. I just wrote the number. Now, this did make a dramatic assumption. It made the assumption that I knew standard deviation. But I went out and I did 10 tanks of gas as an experiment for the standard deviation, right? Well, I did the experiment for the mean. I knew the standard deviation. What if I don't know the standard deviation? If I don't know the standard deviation, then I cannot make an assumption of whether or not my curve is really normal. I can no longer use Appendix C. Ah, crap. So, a gentleman by the name of W.S. Gossett, in the late 1800s, early 1900s, was working with very small samples. And he knew, hey, I don't think these come from normal populations. And he designed a new PDF. Now, at the time, Gossett worked for a brewery. And like most businesses, his employer didn't want private information leaked. When he published his results, they made him redact everything. As a matter of fact, they made him take his name off of it. So Gossett wasn't allowed to publish under his own name. He was required to publish under the name student. Gossett worked for the Guinness Brewing Company. So later on, when you want to celebrate your statistics results, go have a Guinness. Gossett wrote a distribution that kind of looks normal, but it changes depending on how many samples we have. So he changed this curve. Instead of our normal distribution, he drew a curve that was a little different. Notice, when you only have 3 samples, the tails are up higher and the top is down lower. So instead of using a normal distribution, I get this kind of shrunk, squatted out version. And if I have more samples, well, then the peak kind of grows up a little bit further and gets closer. And the more and more samples I take, the closer Gosset's result looks to a normal distribution. But he had this extra number. It depends on n. And this version is called a t distribution. And it's known as the student's t distribution. Now, there are actually formulas for the t distribution, but because they depend on so many different things, the formulas get really ugly really quick. I mean, t distributions look atrocious. Not just no, hell no. We're never going to see that page again. I don't want to deal with it. We're going to have a table or a lookup function in Excel to do t distributions just like we do for the normal distribution. I'm not going to have to calculate a distribution with a function. It's almost always, though, a lowercase t, not a capital T. And you'll see it as the t distribution. The extra thing that tells me the tails is called the degrees of freedom. df is n minus 1. Now, the distribution itself, the tails are bigger. So there's more area out on the ends and less in the middle. That means that t values are bigger than z values when we're out towards the ends. And that means that our intervals get bigger. When we have small sample sizes, when we don't know our standard deviation, we need to give ourselves a little extra room to wiggle on the edges there. And so a confidence interval with an unknown standard deviation is bigger than one with a known standard deviation. Confidence interval for t is wider than for z. Always, 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 always. When the degrees of freedom is small, z and t are substantially different. But as the degrees of freedom get bigger, we get closer and closer to those two numbers being the same. What that means is that when I have a small number of samples, or when I am working with less information, I change out of the normal table. Now, in our textbook, that t distribution table is in Appendix D, I believe. Now, please notice what the top of this table looks like. Here's our confidence level. That's the 1 minus alpha, right? Alpha is this next number. and half of it is on the left and half of it is on the right. So here's the half of it. So they have all of these columns in both versions, whether I'm looking at the left side or the right side. So if I said a 95% confidence interval, my alpha is 0.05. But half of that is on the left and half of that is on the right. And then I can say, well, how many degrees of freedom? If I'm doing Guinness's work, I'm doing Gossett's original result, he was working with 3 samples. That number is a whole lot bigger than 1.96, isn't it, Nico? And I have to keep going down and down and down. And notice these numbers don't get very small. They don't get closer to 196 until I'm way up on my degrees of freedom or over 100. I'm at 1.98. I have to have a really big sample to get closer to Z. And that's why way down here on the very bottom, where that says infinity, these numbers are the numbers from the Z table. But that's this first column in each of these is how many degrees of freedom. The gas tank problem I was just doing had 10 samples, right? So if I had done that problem with 10, instead of using 1.96, I would have used 2.228. Again, put a post-it in the back of the book. If you've got the Canvas page pulled up, table D is available to us in the data tables already posted. In Excel, you use a command that looks like this. T.inverse.2t. 2t? Yeah, there are 2 tails. The part on the left and the part on the right. Then you put the alpha, not 95, you put 0.05, and then you put the degrees of freedom. Under the distributions on our graphing calculator, it's the inverse T, INVT. It's available there as well. There's an older command without the word 2, without the 2t on it. And if you use that one, it actually, you need to put in the 1 minus alpha. So that one you would put the 95% on. But then I can do the same thing. My confidence interval I would need the standard error here, right? Instead of Z, I use T. But then I'd need the standard. I don't know the standard error. Oh, crap. How did we get the standard error, Roman? Right, but I don't know the standard deviation by default. I have to compute the standard deviation. So instead of using sigma, I use S. That's the standard deviation I find from my samples. And I do minus and then I do plus. So I'm just going to write plus or minus here. We'll get one below and one above. Huh. That bookmark back here. I can find that again with that table. Let's pull an example. Like my gas problem, I get a sample of 10 items. And I look at my 10 pieces of sample data, and I compute the mean and the standard deviation. And I come up with, oh, the mean is 270, the standard deviation is 20. So now I can ask the same question. That's an approximation. That 270 is an approximation of the mean. This is an approximation of the standard deviation. If I want to be 95% confident, where is an interval for the true average? How do I find that? I need the appropriate value of t. So, turn to your table in Appendix D, open it up on your computer, or open Excel, and let's use these commands for the t. First question, if I'm going to use that t table in Appendix D, what are my degrees of freedom? It's n minus 1. Always here, my degrees of freedom for a t is n minus 1 is 9. So that really looks very bad. Let's rewrite that 10 minus 1 there. So I go to the line with df equals 9, and I find the 95% value. What's the value in that column? By the way, in Excel, in my calculator, distributions, there it is right there, inverse t. I need 0.025, 9 degrees of freedom. That's what you said df was. And I get this command, and there it is, 2.262. Now, why did it give me the negative value? It gave me the number that was negative because it's looking to the left first. Okay. Because I'm going to add it and I'm going to subtract it. So I'll get both the left and the right with the same number. I take the average from my sample, then I add or subtract the t value, and then the standard deviation from my sample over the square root of n. Yes, ma'am. Instead of the other symbol? Because the other symbol was given to us to start with, right? When I was told up front, hey, you got a standard deviation of 0.33, I didn't come up with that. This S came from my sample data rather than from some other procedure. So all of the information in this problem comes from just the little group I sampled. So I could say, hey, where is the actual average for the exam I gave using you all as a sample? But that's assuming that I give that same exam to a bunch more people, a bunch more times. I don't do that sort of thing. So I can't really, this is a population, so technically these are mu and sigma, but in general, this would be a sample, wouldn't it? You're welcome. I need two numbers. Yes, ma'am. Now notice, 270 is right in the middle of that. But the actual average of the whole population could be as low as 255.7, as high as 284.3. I don't know if I look beyond my sample what the rest of it does. What if I wanted a better estimate? Let's just think in general terms. I took a sample. How could I make my calculation more accurate? I could take a bigger sample. And if I take a bigger sample, that means I make the number I'm dividing by bigger. What happens when you divide by a bigger number? You get something smaller. So if you increase n, your interval will get smaller. You'll be more confident as to where the average really is. I have two of these problems done in Excel that I will post to our sample problems section so that you can see those calculations done there as well. All of this focuses around the idea of a confidence interval for a mean. All of what we have been doing between Monday and today has been based on looking at a mean. And that made sense because a bunch of the questions that were on the exam were about normal distributions, and these are kind of normal-ish. A student T is pretty close to normal. The other distribution we used was on the exam. Uniform. And uniform didn't have a mean, it had a proportion, right? Like our binomial. We had one fraction that gave us the uniform result. Our binomial had one chance of success or failure, right? Well, what if I try and do an experiment and I want to figure out my confidence interval for that? So I go and I do a binomial experiment. Ding, ding, ding. I flip my coins, whatever it is. But I don't know the chance of success or failure. I just know what happened when I did the experiment. I want to know if this coin is fair. Go flip it 20 times. I want to know if this die is fair. Go roll it 100 times. Sounds kind of boring, doesn't it? I want to know what's your chance of success or failure at something. We called that pi when it was given to us for the whole population. That's the theoretical version. But there was an experimental version of this, right? You do the event, and you see how many times the thing you wanted happened. Out of that's our theoretical probability. And that's P, X over N. And in one sense, that's the average of a binary variable. It was either 1 it happened or 0 it didn't. If I think of this as a discrete random variable, then I get some binomial looking distribution. But if I think of it instead as continuous, then the distribution for that approaches a normal distribution. With mean pi and standard deviation sigma sub p, sorry, not standard deviation, standard error. So again, I get to say that if I am doing an experiment over and over and over and observing my results, then I should be getting closer and closer to the theoretical average chance of success as I do the experiment more and more. My practical experiment empirical probability gets closer and closer to the true theoretical probability as I do more of an experiment. Even if I don't know what that proportion is. I do 5, and I get this distribution. 2 here, 3 here. I do 10, I get this. I do 20, I get this. I do 50, lo and behold, I get a distribution that looks freaking normal, doesn't it? Well, binomial. That's pretty close to a normal distribution. So I go ahead and I do samples over and over and over and over again. And the more samples I do, the closer I get to a normal distribution. If it's normal, what table can I use? I can use Appendix C. I can use that normal distribution table. And that means as long as I do enough samples, I can make this a normal distribution. Most of the time, though, I only get one shot at something. One shot at the exam. So I really only get one sample. In order for me to assume it's normal, I need to make it big enough. How big? How big do I make this n to make sure I have enough samples to get a good behavior here? Well, that's going to depend on my chance of success and failure. Ideally, I would like to have the number of successes be at least 10, and I'd like to have the number of failures be at least 10. But if I'm doing something where the chance of success is only 1 in 500 or so, it may take a lot of failures to balance out 10 successes, wouldn't it? So the size of my sample, the number n, is going to depend on my chance of success and failure. Most of the time, I can get close to this by estimating from my small sample based on what I think my chance of success is as to how many I'm going to need. I said 1 in 500, right? If I need 1 in 500, I'm going to need 5,000 samples or a sample of size 5,000 to be able to ensure that I get at least 10 successes. This appears on page 294. But notice the standard error, just like with sigma, it gets smaller as n goes up. So taking larger samples gives me closer and closer estimates. If my sample size is too small and I cannot assume that I have some sort of normal behavior, I can't do confidence interval with appendix C. I need to do it with the binomial instead. And that's a crap ton harder. We're not going to do that. Notice that my confidence interval idea carries over the exact same way. This is my new standard error. Roman, it was sigma over the square root of n, right? I don't have a sigma in this. Instead, I have p times 1 minus p. It's still over the square root of n. But again, I'm assuming this is normal. That's why there's a z there, not a t. And this, d alpha over 2, that's that same confidence level we were just talking about, wasn't it? If I want to really be confident I'm going to get a big interval, to be sure it's in there somewhere. But there's another way to think of this. Another way to think of this is something I'm sure you've heard if you've been listening to the news at all in the past 3 or 4 months as they talk about all these stupid surveys for the election. Every time you see a survey on the news, or you hear it on the radio, or it comes up in one of those ads you're listening to, pops through on your Spotify playlist for a second, or on YouTube or whatever, what do you hear mentioned in your polls, in your surveys? You hear a margin of error. Your margin of error is based on this number. That's where this is coming from. That's our margin of error. The only way to decrease your margin of error is to increase the size of your sample. On page 296, table. If you want a margin of error around 3%, you should be taking a sample size of approximately 1,000. Almost every presidential poll on the face of this country uses a margin of error of 3%. They didn't pull that number out of thin air. Which means, in order to tell a presidential poll, they only have to talk to 1,000 people. Because as I go up in number, it's only the square root of the division. So since I'm dividing by the square root of 100, I'm only dividing by 10. So I'm dividing by the square root of 1,600, I'm dividing by 400. That's a 4 times decrease, right? So instead of going down from 9.8, it goes down by a factor of 4. And I have to get much, much bigger to get that to be smaller. Now, I run right up against the clock for an example. We'll do an example of this on Monday. And I should be able to finish this chapter by then. So that means there's another homework coming up at the end of next week. I hope you all have a wonderful week. If you came in late and I still have your exam, please come get it from me. Otherwise, I will see you all on Monday.